maybe you may wonder why should we study classical mechanics, right? That's a fair question. Do you have an answer? Or I mean, after all, we know that the world is not classical. It's quantum, right? You already, right? So why should we study classical mechanics? This is not a historical, historically is where we started from classical mechanics, but who cares? I mean, you don't start from the history of physics when you start the study. So why should we spend time on classical mechanics? That's a perfectly fair question. And I guess there are two answers, but maybe you want to give an answer before I give my answers. Why do you want to study it? So let's turn it around. Yeah. Okay, that's a good question. Even though you may consider that very often more basic things are more difficult than more advanced. Have you ever thought about that? For instance, quantum mechanics that you have been studying for, what, 4 weeks now? The mathematics is simpler. Maybe you don't agree because you hate it already, but if you think the mathematics of quantum mechanics is just linear algebra, right? Vectors in some space and a product of vectors. This is usually simpler than classical mechanics that is always differential equations. Much harder. But that's very often what happens in physics, that we start from problems that look simple, but really to solve them we need a very complicated mathematics. For instance, even in quantum mechanics, where we started with quantum mechanics, from the spectra, right? Atomic spectra, so the interaction of light with matter, and that's a complicated problem, much more complicated than what you start with now, that is the harmonical oscillator, right? Something like this, you must have done that. And that's a much simpler problem, but that's not the way history goes. I mean, very often we start from complicated problems, and only when we completely understand them, we reach that point of view that is really simple. So, but okay, that's a good point. Any other suggestions? Why do you want to study classical mechanics? Because they told you that you have to, I guess, right? Okay. Okay, I have another reason, in addition to what your colleague told you, is that if you think about it, let's say classical mechanics, okay, is really what we fully understand. At least is what I fully understand. Because when you have a classical mechanical model of a process, you really understand it, right? Maybe in terms of springs, point particles, some device, but you really understand what's going on, right? Because we really have a profound insight into classical systems. You cannot say the same about quantum mechanical systems. Quantum mechanical systems, you know, probably already, they are very complicated to understand because they are not, it's a statistical system. There is probability of something to take place, right? And have you done Schrödinger equations? Right, you have already studied. And okay, you know what the equation is, you know how to solve the equation, but do you really understand what's going on? No, I mean, nobody does. I mean, this fact that the electron goes through two slits at the same time, that you have superpositions, right, interference, that's very hard to understand. And in fact, we don't have intuition on that. That's why we rely on mathematics there very much. I mean, we cannot guess the answers. We have to work out the answer through the mathematics, and that's why we study mathematics. It helps us to understand the problem. Classical mechanics is more, we really, after a while, I hope, by solving many problems and other stuff, you really develop some feeling for the things. And then you will see in your career as physicist or well, I don't know, I assume you want to become physicist or not? What's your ambition in life? I hope, you will see that you will always come back to classical mechanics, because that is a rock solid, is what you know. You will compare any solutions that you are going to find for new problems in terms of what you know in classical mechanics. So that, for me, is one of the reasons why it's so important to understand classical mechanics, I switch. Even though, as I said, that's not what how the world is made of. The other reason why we start from classical mechanics is that many concepts and techniques that you are going to use in other fields of physics were first developed in classical mechanics. After all, we started from there. And many, many things like differential equations, special functions, well, you name it, everything essentially that you study in Narayan's class was first developed in classical mechanics to solve problems. So that is a nice place. It's like it's a test ground for these mathematical techniques where you can apply them and understand a lot before applying them to more complicated problems, okay? So that's the other reason. So you will see we will meet many techniques that you probably already study either in the mathematical methods class or in quantum mechanics. They first come in here, and we will study them in classical mechanics to understand how they are arised and why we use them, okay? So in other words, I think both the conceptual frameworks of our understandings of the physical world, okay, and the techniques that we use to understand the physical world, that is the mathematical techniques, they were first developed in classical mechanics, and it's still useful, I think, that we learn them by studying classical mechanics. So that's my justification for this class. Is this clear? Should I talk slower or? It's clear. Maybe I should also mention that a lot of modern physics is still classical. Maybe we should say that. It's true that the world is quantum, but say gravity, right? The gravitational force is still a classical force. We don't know, we don't even know the quantum theory of gravity, but for all practical purposes, it's classical. I mean, we send a man on the moon. Well, the NASA people send a man on the moon using classical mechanics, actually using Newton's law. They didn't use Schrödinger equation, right? 90% of what you do is in the classical world. Maybe it was 99% just 20 years ago. Now we cannot say that is so much, because so many devices now that you use from your cell phone, the GPS locator, you name it, they are actually based on quantum mechanics. So now you know a lot of quantum mechanics just by looking at many of these devices. But say 20 years ago, everything, 99% of our world was classical. Well, there are many examples of classical systems that we use every day. I mean, your car, the bus you ride, I mean, that is well described by classical mechanics, right? You know that as long as h bar, Planck's constant, is very small compared to the characteristic energy of your system, classical mechanics is very good, right? You know that sort of the domain of classical mechanics is between systems in which the energy is much larger than h bar and systems that move at speeds that are much less than the speed of light, right? Because if you approach the speed of light, then you have to worry about relativistic corrections. So classical mechanics sort of goes into relativistic mechanics, and we will be doing that next semester, or I mean after Christmas, because I'll be teaching you also the classical electromagnetic theory, so always classical. I like classical physics. And there we will talk about relativity, necessary, because electromagnetic waves move at the speed of light. So there you are forced to address what are the laws of physics when you move at speeds that are close to the speed of light. But up to Christmas, we don't worry about that. Our speeds are much less than the speed of light, and our systems are big enough with the energy large enough not to worry about quantum mechanical effects. Okay, we don't talk about atoms, or we will talk a bit about atoms, but in a classical manner that we will see. Okay, so that's what I wanted to say as a general introduction, and maybe I'll tell you what we are going to do. I mean, the main subjects that I wrote here, so it's sort of an outline. I should not write above the line, right? Okay. So this is the outline. So we have 20 classes, or 1 hour and a half. If you agree, I teach 1 hour and a half and then I stop. Or do you prefer that I teach 45 minutes, then I stop? Do you understand? No, you don't understand, or no, you don't want to? What? Right, I mean, so that we finish earlier. I know that is kind of, I mean, I know that you already had George for 2 hours, so you must be pretty tired, but I don't know what to do. I mean, I come last, and so, but if you are really tired, tell me and we stop, because it's useless to keep going if you are. I know that after 1 hour, one is already saturated, and there are many studies that tells you that actually half an hour is the most of the attention span. You know, attention span. I mean, how long you can follow something. I don't know how much TV do you watch. I mean, the attention span has been proved. I mean, it's inversely proportional to the amount of time you watch TV, right? I mean, if you are a kid who watches like 10 hours per day, then your attention span is 5 minutes. No, it has been proved. If you don't watch TV, you know, like in the old days, people were used to lectures of 3 hours, not following really. So you have your pick. Stop watching TV. Okay. So as I said, we start with what I call the Lagrange equations. Okay, if you know what that is, good. Otherwise, we will talk about that. And after we develop this, it's a sort of alternative frameworks compared to Newton's law, okay? So you can do, probably you know about Newton's law. We'll talk in a second about that. You can solve all problems in classical mechanics by using Newton's law, but there is a more efficient way, and this is called the Lagrangian, okay? So my aim here is to teach you a more efficient way to solve the same problem that you have solved at the undergraduate level, because now you have to move to the next level to become a professional physicist, and you cannot use Newton's law. I mean, it's too complicated. It is not efficient. So you need a new technique, and this technique is this, okay? So Newton's law is like the old radio with these valves and stuff, and Lagrangian is like the transistor. I mean, it allows you to solve many more problems in a fraction of the time you used before. Then we will sort of spend some time on a very important subject that is conservation laws. Okay, these are, you already know that they are very important, and you will see why in a more detailed way within the framework of the Lagrangian. Okay, they really help. These conservation laws help us in solving problems, in understanding the. And of course, after you write equations, you want to solve them, right? And this is called integration. These are differential equations, so integration of equations of motion. This is really where we are going to spend most of the time, right? Because by integration, I mean solving the equations of motion. So we will solve many examples, and these examples are sort of canonical. I mean, you find these in all textbooks of classical mechanics, and usually are, say, the motion, they are called motion, so the motion in a central field. This is also called the Kepler's problem. Have you heard about that? I mean, why it's important? Well, this was really one of the first problems people tried to solve because, for instance, the motion of our planet, Earth, where we are around the sun, this is an example of the motion in the central field, right? And in fact, that was exactly Kepler's problem. How our planet moves, right, about the sun? It's in a circle. It's a more complicated path. We'll see. Then usually we will see how much time we have. Collisions. I like to talk about collisions, scattering problems, but certainly then we will discuss what is called like a small oscillation. This is another very important subject. Small oscillations means motion about some equilibrium point that is well described by harmonical oscillators. And you already know that this is very important. Why it's very important? Why these two problems are very important? They are very important because we know an exact solution. We know exactly how to solve the harmonical oscillators. We know exactly how to solve the motion of a point particle in a central force field, right? And there are very few problems around of which we know an exact solution. So you have to treasure them because every time you look for a new problem, you always start from something that you already know, and ideally something that you know exactly how to solve. Okay? I mean, 90% of the problems, we don't know how to solve them exactly. We solve them numerically, by approximation. We use perturbation theory. But few problems, and these two are those few. I mean, there are not many. You can count them on the fingers of one hand, and you don't even need all 5 of them. Think about it. And so you really want to know them by heart, because those, you know how to solve them exactly, so that's good. And then the motion of a rigid body. We will define what we mean by a rigid body, and then we will solve the motion. This maybe is not such a, I mean, it doesn't have many applications outside classical mechanics, but again, has played an important historical role in the development of classical mechanics, so maybe it's a good idea to spend some time studying that. And then we will end with what is called canonical equations. That is another way, similar but not identical, of doing classical mechanics that is not quite Lagrangian. Okay, so this is one way, and then at the end we will come back to the general problem of solving classical mechanical problems and try to solve them in a different way that is called usually the canonical equations. More specifically, it's called the Hamilton, or maybe, yeah, Hamilton's equations, and even Hamilton. These are all Jacobi equation. This is just one. Different ways of solving the same problems, okay? And you will see this is a very elegant way to solve the same problems, and you may learn something new that is then it could be useful. Have you ever heard about this? Hamilton is the Hamiltonian, is the same guy. And Hamilton Jacobi, maybe not, but we will. Okay. How about books? Have you what books have you used in your undergraduate studies for classical mechanics?
Goldstein.
Goldstein, okay. other books. So we will use the Gauss. Well, I will use my notes, but essentially these notes, they don't come out from. I just use some of these textbooks, and I think the Goldstein that he mentioned, Goldstein, classical mechanics. Now I think there is a third edition or something that is not just Goldstein, but there are two other authors that I forget. But if you go to the library, you have here a wonderful library with many books. You can find the latest edition, and you can take it. Actually, many of the problems that we will solve together come from the problems given by Goldstein. Okay. And the other book, it's a little bit older. You know Landau? Have you heard this famous Russian physicist? And he wrote a famous textbook together with Lifshitz. Well, I'm not sure about the spelling. Lifshitz, just mechanics. Actually, they wrote an entire curriculum on physics. They wrote a textbook for most of theoretical physics. There is also quantum mechanics, quantum field theory, and so on. And the first volume of this series is called Mechanics, and it's a very good introduction, even though it's a bit, maybe as a first reading on the subject, it's a bit difficult. But it's a very good summary. It's a small book. Also, are you, any of you are Francophone or Francophone? So there is also the French translation that, so you may like it. Okay, so essentially these two are the books that I sort of use to inspire my notes, if I can say that. So in other words, what I say, you can just take these books and study by yourself, and you'll be fine. Or you can come to class. It's okay. I mean, I won't be offended because I'm not doing anything more than what these guys did in their books. I mean, certain things that they said very well, so there is no way to improve, so I will just repeat whatever they say, and then they will tape it. Okay. Maybe I should also say a word about exercises. Sorry, and problem solving. As you know, in physics, you have to solve many problems. Okay, it looks very boring, but there is no alternative. I would say 70% of what you are supposed to learn does not come from frontal lectures like this, comes from you solving a problem. That's the way of physics. I mean, there are other subjects, I don't know, that I'm not familiar with, like philosophy or history, where probably, I mean, the lecture is the most important part. But in mathematics, in physics, in many scientific disciplines, the most important part is not what I tell you, is what you solve by yourself, solving the problems that I tell you to solve. Why is that? Well, because physics is a little bit, as you probably already noticed, is like something that you learn how to do with your hands. I mean, if you have to learn how to play tennis, I don't know, you know tennis, or any other sport, I mean, there is that much I can tell you. You know, I tell you, hold the racket this way, move this other way, but I cannot teach you how to hit correctly, right? You have to exercise many hours every day, okay? And after you exercise many hours, many days, you become very good, maybe. The same is in physics. I mean, you solve many problems, many problems. It looks very boring, as it is boring to play tennis, you know, many hours every day, but there is no way around. If you want to become a champion, you have to play, you know, practice tennis 10 hours every day. And the same ideally here. You should solve problems well, the one I will assign you, or whatever problems you find in any other books you like. And this is the only way to learn how to do physics. Because if you think about it, you talk to somebody, you ask a question, and this somebody tells you the answers, right? And then you say, oh, he has a very, how do you say, a physical insight, right? Because it told you the answer. But where does that come from? He was not born with a physical insight. Simply, he had solved many more problems that you had. And so when you ask, he remembered that problem that was similar to what you were asking, and he knows the answer. So what you should really strive here is to solve as many problems as possible. It's good to come to the lectures, but it's not the most important part. The most important part is to solve this problem, because that's the way you learn how to do physics. It's also the way we teach you how to do physics, because it's not something that you teach. It's something that you show how to do, and then you imitate, and then you learn, okay? It's a bit like medicine. The surgeon does not really teach how to cut and how to do surgery. You just show, then you try, and you learn, right? So it's something that you show, as you see, you learn. And the same is here. You will see me struggling through some problems, and I hope this will inspire you to solve the same problems and to learn how to do it. And in the process, you will become a physicist, okay? Whatever that is. Okay, so have you any comments? Otherwise, I finish with my introduction. Do you think? What? Tutorial. Okay, good. So instead of having a tutorial, what I do is, since I don't have a tutor to solve the problems, and I have to do everything, so what we will do is this. Usually on Monday, so I will give you, during the week, I will assign you some homeworks, okay? And then the Monday, usually, we spend solving the problems together. And by together, I usually mean I ask one of you to solve the problem, and all the others to help, myself included, and we solve the problems, okay? So now, not this Monday, because probably we won't have enough material to do homeworks, but at the end of every lectures, I will tell you what problems to try and solve. Then you have time over the weekend, over the week, and then every Monday we try and solve the problems, okay, if you agree. So we will do it this way. I mean, any other question? No questions. You are tired already, I can tell. You should ask George to stop at 3:30. I always tell him, but he keeps on going, right? But at 3:30, ask him to stop so that you have half an hour before I come in. I think it's otherwise too tiring. Okay, let's start from something that I hope everybody knows. Is this. What is this? Right. So this is what we start from, and as I said, there is no problem in classical mechanics that you cannot solve by using this. Everything is in there. We know. Newton already did it for us. And actually, this is a highly non-trivial equation, as I hope you realize. First of all, let me ask you, what is the unknown here? I mean, when you write F equal to ma, what is given by the problem and what you are supposed to find out? Is F or m or a? Or any motion, right? But my question is very simple. It's not a trick question. I mean, don't worry. I never ask 3 questions. I mean, you have, so it's a differential equation of what order? Second order. So here there is the second derivative of the position, a vector in space. But my question is, if I give you a problem, say the usual spring with the mass attached, whatever, by giving you the problem, which part of this equation I'm giving you? This? No, I don't agree. Yeah. Right. But if to describe the system, I describe you a system. So which part of this I'm not giving you the acceleration, because that is the solution, right? So what I'm giving you is the force. This defines the system. I mean, this is the same law for any system. You give me the system, I write the equation. You give me another system, I write another equation. But the system by itself is, for instance, I give you the chalk, this is chalk. And I say, how long does it take for the chalk to hit the ground? So in what sense well, now it's gone. Okay. Oh, I broke. By the fact that this chalk is here, right, in the gravitational field of the Earth, that means I give you this, right, mg. In fact, this is a very famous example, right? I have a point chalk. I mean, it's not really a point, but never mind. And I write the force. Now, this is the equation I'm supposed to solve, okay? So every time I give you Newton's law, you have to translate the problem in terms of force, or forces, depending. And then you write the equation, and then you crank in, because this is the second order differential equations, and you know how to solve that in many cases. And already here you know a very important thing, that the mass, I mean the time that a body takes to hit the ground does not depend on its mass, right? This is highly non-trivial. I mean, if you ask anybody around, try on the bus, if you come here on the bus number 36 or whatever, ask if you have a very heavy ball, right? And then a feather, no? You drop them at the same time, right? Which one will hit the ground first? I think 90% of the people will say the very heavy ball, right? Are you a physicist? Or so what would you say? If you have a very heavy, of rock, and then a feather, una penna, no? And you drop them from here, which one will hit the ground first? Okay, but he knows. He knows already too much. So you should ask somebody who knows less. But I mean, our intuition is that, and it's not so far wrong, because we are used to frictional forces. We know that there is air, and we know that this is the reason why bodies fall at different speeds. But Newton's law, exactly because you can drop this mass here, you have it on both sides, tell you what he said correctly, that they both reached the ground at the same time. What happens if f is equal to 0? I can define a system in which f is equal to 0. There are no external forces. Maybe a vector 0. That's, again, this is a sort of uncommon situation, because in our world there are always external forces, but you can always think to bring a body very far away from any planets or any stars, right, is the ideal situation in which you don't have any external forces. Then this is the other non-trivial property of Newton's laws that tells you that if you have a body with no external forces, right? For instance, you are pushing something, no, a body, a mass, and then you stop pushing. So you stop pushing, so there are no external forces left. What happened to that body? that is another question that I'm not asking again because, but it's another point where most people will say, if you stop pushing, the body stops, right? But this is not what Newton's law is telling you, because that would be true if you had this equation here. If that had been Newton's law, then it's true that if you stop pushing, V must be equal to 0, so the body stops. And that for many years was the idea, because people, I mean, after all, if you try pushing something, right, and you stop, then it stops. So it looks like the law is F equal mv. And it was really Newton or Galilei, I don't remember, one of these old guys, who first realized that the correct law is this one. And this is a tremendous consequence that, in fact, if you stop pushing, stuff keeps on moving, right? So in other words, there is no way to tell if something is at rest or it simply moves with constant speed. And in fact, for physics, for classical physics, it doesn't matter. They are completely equivalent. For us, a system that is at rest or it moves with constant speed is completely equivalent. In fact, they are, you can transform from one to the others. The physics is the same. Now, you understand that this is very important because we are in one of the such systems, right? Because as I speak, you know that we are moving about the Earth is rotating about its axis. You know that it's a quite substantial speed, right? It's like, I mean, here on the surface it's like 30 meters per second, 30 kilometers per second. And at the same time, it's moving about the sun even faster. So we are moving a lot, but we don't perceive any of this, right? If I drop this again, it doesn't fly off that way 50 kilometers per second. It simply drops as if I was at rest. And this again is true because this is true. If that were the law, it would not be true. So this was a gigantic step that humankind took by understanding that Newton's law is Newton's law, F equal ma. And they, you know, the ancient Greeks, the people living in Greece many, many years ago, they thought that this was the correct law, simply because they try and they you know, if you try, you have to keep into account frictional forces, and many phenomena are dominated by frictional forces. And frictional forces are forces in which you have V, right? Because if you push, stuff tend to stick. Okay? So maybe I should say but probably you already know that all these systems that are either at rest or move with constant speeds are called inertial frame of reference. You heard that. And when we talk about physics, we talk about this. I mean, classical physics, we talk about these frames. But essentially, the meaning is a frame of references in which Newton's law is valid. In fact, we will see that there are many interesting systems in which Newton's law is not valid because there are apparent forces due to the motion of the system. There are many systems, right, like that. Any rotating system is not an inertial system, right? And you know that there are many forces from Coriolis, centrifugal forces that we will study that are there exactly because you are not in an inertial frame of reference, okay? The bus you ride, number 36, again, is not inertial because it stops, it accelerates, and you are pushed right back and forth. So it looks like there are no external forces, but still you are accelerating. That's an indication that is not an inertial frame of references. So that's what I wanted to say about things that you are supposed to know already, Newton's law, namely. And then we mentioned that because of Newton's law, we have to do with second-order differential equations. So let me just remind you, don't feel insulted if I remind you of something that is trivial, that first, to have a differential equations, you need a time parameterization of the position of your object. This seems trivial when you write that the position, say just a point in one dimension, is x of t, right? X is the position as a function of time. This is what is called a time parameterization. This idea, too, is very deep. Stop for a second and think about it. I mean, it's highly non-trivial that you describe the motion of something in terms of a trajectory, that is x of t. Because the first time you see the motion of something like this, you don't think of x of t of this something. You think of the motion as a whole. If they ask you to describe the motion, I toss this chalk there, you describe the trajectory, right? But not as a function of time. This was a great idea that they had. And they had people, I mean, our colleagues, well, I guess it was Newton again, was the first one to realize that if you describe the trajectory not as a whole, you know, as a whole, I mean, I toss this and I say it's a parabola. It went up and then down. Okay, true, but so what? But he had the idea that if you parameterize the motion through x of time, that you flash time like this, at each instant you give the position. This is a very powerful way to describe the motion, because then you can apply a differential equation. Because a differential equation is that's something that tells you that if you know how or where the body is at time t, tells you where it is at time t plus delta t. And if you know that, delta t, delta t. So you rebuild the trajectory one step at a time. That's why it's called differential equation, right? This is a very, very powerful idea. And when this was developed, really opened the doors to classical mechanics, because we know that we know about classical mechanics through the solution of differential equations. So you have the position, you have the velocity. Sometimes I use this notation that, again, is due to Newton's, that if I put a dot, you know this notation. A dot means the first derivative with respect to time. Two dots, second derivative. So x dot is exactly dx of t dt. So we said these are second order differential equations. So that means that you have two derivatives, what we call the accelerations, then you have one derivative, and so on and so forth. So they are equations in this form, right? The acceleration, like ma equal f. And the thing I want to remind you is that because they are second order differential equations, you need two initial conditions, right? Completely, you need the initial condition, say the position at time t naught, but that's not enough. You also need the velocity at the same time, right? You also need x dot at the time t0, okay? If you specify that, you have completely specified the system. You can solve the differential equation if it's one of those differential equations that you know how to solve. I mean, there are not that many, again, but let's hope that, of course, in all the problems, we always end up with differential equations that we know how to solve, and then you find the solution. And the solution is the trajectory, and then you have solved the problem. So how do you solve a problem? So again, here, let me just say something that is very basic and that I hope you already know very well. Now, the typical problem is the one you find at the end of your textbook, and they ask you, given the such and such. So the first thing I suggest is that you draw a diagram. Draw a diagram. This is very helpful. You know, you draw the little mass, you draw the forces, some stuff like this. I'll show you. Okay, I mean, you can do it. You don't have to do it, but very often it helps you, right? You always have stuff, say you have a mass on a wedge, a mass of mass m, and this moves in the direction x. This is what I mean by drawing. Just draw And when you draw, I suggest you write down, so write down, this is really, I mean, write down what you know. And what you are trying to find. This is what I did before for F equal ma, right? I asked myself, what do I know of this equation? I know the force. And what I'm supposed to find out is the acceleration, okay? Or by integrating the trajectory. So every time, write down what you know and what you are supposed to find out. This clarifies the problem, because sometimes you are lost. You write something that it is a variable, then you put it as an unknown, and so on and so forth. And at this stage of the problem solving, try not to plug in the numbers. By this, I mean solve the problem symbolically, okay? So solve things symbolically. By this I mean give a name to the variables, give a name to the unknowns, solve for the unknowns. Don't plug in. If I tell you a mass of 3 kilograms, don't write 3 kilograms. It's always best to write everything symbolically and only at the end to plug in the numbers. Okay? You learn more this way because it's more general, and also you have a better feeling of what's going on. So only at the end plug in. And when you plug in the numbers, consider units. Consider units and dimensions. You know what I mean. Any number in physics has some units. I mean, you cannot say 3. You have to say 3 kilos, right? Or 3 seconds, or 3 meters, right? It's like apple, bananas, and you have to say what it is before you eat it. So this is by units. And also the dimensions. You know that not every, but there are quantities that are dimensionful and dimensionless, right, in physics. Right? Seconds, seconds are seconds. So time is in seconds. And the mass is in kilos, for instance. Now, there is a very nice thing that you check out when you do your computations are the dimensions. For example, if you have an equation, you know that the dimensions must be the same on the left-hand side and the right-hand side. If you don't have the same dimensions, you have made a mistake. That's obvious. So that's a way to check. And I'll show you in a second that they are also useful to guess the solutions. We will do. Along these lines is also when you have a formula that is, for instance, you found the velocity as a function of some of your variables, check for the limiting cases. That's another very useful trick. Or limiting or special cases. I'll show you in a second what I mean by that. But that helps you to check if your answer is correct, and is also useful in real life. I mean, if you have a formula, you can immediately see if it's correct, it's an approximation, or simply wrong. And again, in this class, check the order of magnitude. You know what? Check order of magnitude. That is, if you end up getting a number that is billions in a problem in which you have 3, 5, 6 kilograms of masses, clearly you have made a mistake. So check the order of magnitude. That's a golden rule everywhere in life. I mean, they tell you something, check the order of magnitude. I mean, if you go to the bank, check the order of magnitude. I mean, if they tell you 1 million, check. Maybe it's 1,000. That's a very handy suggestions. Okay, so that's my sort of short list of what I do when I'm given a problem in classical mechanics, usually. So I draw diagrams. I write. I don't have to write, but I try to fix in my mind what I know and what I'm supposed to find out. I write everything symbolically, I write my equations, then I consider the solution, and there I consider dimensions, units, maybe special or limiting cases, and always I bear in mind that the order of magnitude, I mean, before I start solving my problem, already I have the order of magnitude of my solution in mind, and at the end I check whether that it matches, I mean, if it's okay. Okay? Did I leave something out? Do you have something that you do that I didn't? No? Now, for instance, let's discuss an example about units and dimension. You know about the pendulum, I hope, right? A pendulum, it's a point mass hanging from a weightless string. So here, point 1, I draw a diagram. So for me, a pendulum is something like this, right? I have a mass, M, is hanging from some ceiling, and there is a string of length L, right? And let's say I call theta the angle from the vertical, and obviously for the problem to be of any interest, this system is in a gravitational field. So I have the gravitational acceleration that I call g pointing downward. Okay? So let me ask you first, what are the dimensions of our variables? So the mass, usually the dimensions are indicated by square bracket, but you have your pick. So the mass, well, this is kind of easy, is a dimension full quantity, right? You agree? And is measured in unit of, yeah, of mass anyway. It's a fundamental, you know, there are many systems, unfortunately. MKS, have you heard about it? I mean, usually you pick 3 fundamental quantities, and all the others in mechanics can be built out of those, right? And usually you take the mass, the length, and time, all right? But you're not obliged, but this is what people do, so usually it's a good idea to do what the majority of the others do. So if you want, the mass is, if I call big M the unit of mass in this system, the mass is, it's a mass. Then that big M can be grams or can be kilos, depending on the system. You know that there is the MKS and the CGS. Okay. We are not really, I mean, this was a big deal, I guess, in undergraduate studies, but from the point of view of theoretical physics, this is not a big deal. I mean, actually, we like to reduce even further the number of fundamental units, and probably you already know that because there are constants that are universal in physics, actually you can reduce this number, right? Have you thought about that? Because you can take as your basic units those constants and then measure everything using those constants. For instance, as I said 1 hour ago, we know that the speed of light, right, c, is a constant. And we also know that h, the Planck constant, is constant and is universal. So you already have 2 quantities that are ideal to define all the others, because you know that those are universal, are constant. So in principle, I could define all quantities in terms of multiple of linear combination, actually of combination of C and H. And because I need 3 quantities, I'm left with only 1 free quantity that I call usually the energy. So everything could be measured in terms of energy and not in terms of meters, seconds. You will see as you progress that this is what the physicists do. They tell you everything in terms of energy. not meters, seconds, kilos. Okay, and this is possible because you have two universal constants. If we had three constants, we could just talk about numbers, dimensionless numbers, because we would just need to say how many h's, how many c's, and how many of these other constants that we don't have, that particular quantity is, and you will know what I'm talking about. So for many years, we wanted these third constants because we really wanted to say just numbers. I would say 3, and you will know what it is. Not 3 kilos, not 3 seconds, not 3. Unfortunately, we don't have these third constants. You're choking. Feel free to cough, because otherwise we have to call the ambulance. Okay, but up to now we don't have this third constant. So we only have h and c. Maybe it's Newton constant. We don't know. But never mind, this is just to... We will stick to the old system that we have 3 fundamental units, mass, length, and second. So as I said, the little mass of this bob here is measured in m. L, the length of that strings, obviously is measured in L, be that meters or centimeters. And how about g? Now, this is a little bit... g is the acceleration. So what is the acceleration in terms of m, L, and t? M? So it's L, right? Because it's a second derivative of the distance traveled. So the distance traveled is L, and the second derivative, right, is d2, so it's a t squared. Okay, this is so far so good. For instance, what is theta? What are the units of theta, the angle? It's just a number, right? That's good. Not everything is dimensionful. Theta is, I don't know, is dimensionless. Dimensionless. Let's call it theta naught. That is the maximum amount by which you pull the bob away from the perpendicular direction. Okay, so this is theta naught. Then you release it, and it goes like this. Now this, you release it, so it starts oscillating. It's a pendulum, and so it is going to have a frequency. What are the dimensions of the frequency? Let's call it omega. What are the dimensions of a frequency? Louder. So per second, so 1 over t. You say, you know, 3 times per second, something like this. Actually, you see, this very simple problem, we will come back to the pendulum many, many times, because it's, again, it's a problem where you know that it is equivalent to a harmonical oscillator within some approximation. So it's a problem, as I said, that of which we know the exact solution. Now, by this information, you can already guess. What is the frequency of the pendulum, right? Because we say the frequency of a pendulum, omega, is dimensionally 1 over a time, right? Now, I don't want to write Newton equation. I don't want to write anything. I know that the frequency must be 1 over time. And my problem has these 3 quantities, so I have to look for a combination of these 3 quantities that goes like 1 over t. And I've solved the problem, right? So what is this combination? So you see, I have, right? Because you see, I take G. Say I take G. So I have L over T squared. The L I don't like because there is no L. So, okay, I divide by little l. And I'm almost there because L, I divide this, so I have 1 over T squared. If I take the square root of this, I get exactly my units. So without solving anything, just by dimensional analysis, I can already tell you that the frequency should be the square root of G over L, a result that you are that I hope you know from somewhere. Actually, if you are really, you could always multiply by an arbitrary function of theta naught, because that guy is dimensionless, so I have no way to prevent it to enter this formula. So in principle, the frequency should be this times some function of that. You know from your previous studies that the frequency is exactly this. There is a 2 pi here that is inside right here. But actually, this is not quite true, and we will come back to this, because that formula that you know is only true for small oscillations. It's only true if you pull this a little bit away, and then you let it go back and forth. If you pull this really high, it's not going to be true. And we'll study this problem. But as long as you stick to small oscillations, this is certainly true. You can forget about this, and this is the result. And you see, just by doing dimensional analysis, you have solved the problem. This is very often, also in real life, people ask you complicated questions. This is what engineers usually do. They are very good at dimensional analysis. So they estimate roughly what is going on by, the stability of a building, by just doing some like that. How about the energy? What is the unit of the energy? The energy, well, think about the kinetic energy. What is the kinetic energy of a point particle? 1/2 mv squared. Everybody knows that. So 1/2 is 1/2. So it's a mass, right, times v squared. V squared is what? Dimensionally, L over T squared. So these are the units for the energy. So from here again, I can guess what is the energy of these things, the system. I mean, I know that you know how to compute the energy of this particle in the gravitational field, but just from here, you see that you have to build up m, so there must be an m, right? And then L over T square. You see, L, G, there you are, m, G, L. Unfortunately, always, but again, let's assume that this is 1 for small oscillations. But actually, this is not quite a good approximation, right? I was expecting some objection. Why? Does the energy of the pendulum depend on the initial or not? The frequency does not for small oscillations. But the energy, it depends, right? Because if I start this from here, or I start it from here, they have quite different energy. So it's not true what I just said. Right? Usually you write it like this, right? And then you expand the cosine. What is the expansion of the cosine? What? 1 plus that. So this is roughly mgl. So it does depend on theta naught. The energy depends. It's the frequency for small oscillation that does not. Be careful. Questions? Comments? So this, well, let me accelerate a little bit. So this was about this point about considering units. So I hope I convince you, at least in this simple case, that it's a powerful technique. I mean, always check the units. Also because that saves you from really, those mistakes that people say, oh, how can you say something like that? Check the units, because that usually stop you way before you write down something completely wrong. How about these other things? Why is this useful? Okay, I give you an example and we discuss it together, and I hope we learn something. Let's consider another problem. So I have a person throw a ball, okay, at a certain angle of her choosing, with a certain speed v. No, the classical mechanical problem. But from the edge of a cliff of height h. Is that clear? No. So I draw number one. So I have a person. Well, okay, my drawing. Okay, this is. And he's throwing something with initial velocity v, but is standing, okay, at the edge of a cliff. A cliff, like Assistiana, and the height of this cliff is h. So this is the drawing, point 1, and I write down everything. So I know v, I know the height of the cliff, okay? And the question is, what is the maximum horizontal distance the ball can travel? So horizontal distance is this one. So what is the maximum distance, horizontal distance, this ball that you have thrown with initial velocity v, standing on top of a cliff of height h, can reach? So it's the usual problem of the cannon firing something, but with a twist, and the twist is the height of the cliff. And I don't want you to solve this problem now, but I give you a number of solutions. So I guess I can remove at least these two. So let me write possible solutions, and then I want you to pick one. I mean, only one of these solutions is the right one. It's like a little game. So I'm talking about this distance here, the maximum distance as a function of v and h, and of course g, because so this is a possible solution. This is another solution. Here I have another solution, and then an even weirder solution here. Maybe the same, but without the square root. And then a final one. So this is the problem. I mean, that is the problem. And instead of asking you to solve the problem that you are supposed to know how to do it just by using Newton's law, I give you 1, 2, 3, 4, 5, 6 possible solutions. Now, which one of these is the correct solution? Well, let's look, I say, check limiting of special cases. This is a way to check the solution. Let's assume that you have worked out the problem and you end up with that solution. Are you confident? And you give me that as the solution or not? Well, you see, let's take for instance, what is the meaning? Let's take a limiting case. What is a limiting case? For instance, let's consider the same problem, but in the limiting case in which the cliff is not there. That means h goes to 0, right? Now, this solution, if I take now, so I take this solution for h going to 0, you see that this goes to 0. Is this reasonable? No. I mean, even if I'm not standing on top of this cliff and I throw the ball is not ended up at my feet, right? Still, it will fly. Maybe less, probably less, but still it will go some distance. So this solution cannot be right because it makes no sense. Right? You agree? So you see how you use limiting or special cases. You look at your problem in a special situation, for instance, no cliff. I still know that this guy will throw the ball some distance, so it cannot be that the solution goes to 0 if I take h going to 0. So that's wrong. Better not give this as an answer. How about the second? So this is gone. How about the second one, v squared over g? What is peculiar about this solution?
The order of, it increases very rapidly for large values of b.
Okay, but that could be, no?
Yeah, but with some...
But? Yeah, but what is even more... Right, I mean, do you agree? I mean, this is very weird again, because again, I know that if I'm standing on top of a very high cliff, I mean, that my thing will fly, I mean, I guess it will fly further away than if I'm not standing on top of a cliff. So the solution must depend on h somehow. Not in the way the first one depended, that was directly proportional, because that I know is wrong, but it cannot be independent of h, because the problem, I mean, the solution of that problem, in fact, must depend on h. So this is wrong again, wrong again. This one, I already ruled it out before, because it's not because I make that nice sign of the square root that I'm helping my case. It still goes to 0. It goes to 0 even faster, and so it must go. How about this? This looks complicated. Could be right. I mean, there is h, right? So, okay, it could be right. But can it? What happens if, yeah. Why is this wrong or right? V? But if v goes to 0, yeah? No, okay. If v goes to 0, it's correct. What happened? No, it's not going to infinity. Take the limit. Let's take this limit. So she says, what happened if v goes to 0? Well, what happened here if v goes to 0? It goes to 0. I mean, if that means I drop the thing, so that's exactly the case in which I hit my feet. So I take v go to 0. Okay, first term goes to 0, but how about the second one? It's not. The second one goes to 2h. That's not possible. I'm throwing the thing with 0 velocity, and still it flies off. So this is wrong. How about this one? Why is this obviously wrong? This looks a bit what you said. What if v is equal exactly to square root of 2gh? A possibility. I throw the ball with the velocity that I've been so clever to pick to be exactly the square root of 2gh. You cannot rule it out. It's a possible velocity. But then if that is the case, you hit the pole here, and this is infinity, as you said before. This is really divergent. As you know, I mean, divergent quantities usually, a divergent quantity usually is wrong, right? So we are left with only one, and it looks like, but this we already ruled it out before, but not quite, right? Because we rule out this without the square root. But now what happened because of the square root? What happened if I take the limit v going to 0 this quantity? Before it was different from 0, but now So this goes to 0. Now here you only have one v because of the square root. And so you see this goes to 0 because you have one surviving power of v in front of everything. So this looks to be the answer. It's complicated. It looks very complicated compared to some of the others, but at least this one has a behavior in the limiting cases of h going to 0, right? You see, even if I send h to 0, still this is the result. In fact, this is the correct result if you have no cliff. And if I send v to 0, it goes to 0, so everything looks promising, and I can proceed and assume that this is the correct answer. So this just to say, at the end of your problem solving, look at your solution and try some limiting cases just to see if you are writing something that is completely wrong. I mean, not it's obviously wrong, or something like this may be right, but certainly is not obviously wrong. You want to stop? I guess. Okay, but let's. Questions? Well, let's stop here.